A typical shooting star occurs in a fraction of a second. A fragment of space rock enters the atmosphere at high speed, flashes white-hot, and then vanishes into the dark. But sometimes the sky holds on to that light. A ghostly trail remains painted against the starfield, lingering long after the rock itself has burned away. These traces, known as persistent trains, can last for minutes or even an hour. As high-altitude winds catch them, the glowing streaks drift and twist into strange, fluid shapes. For over 100 years, this physical contradiction has baffled researchers. It is a trail of light with no visible source to keep it burning. In the 1940s and 50s, astronomers believed a persistent train only occurred in 1 out of every 750 meteors. They also assumed that only the largest and fastest-moving space rocks possessed the energy required to leave a mark in the sky. Because early observations were limited by the technology of the time, researchers often set aside these events as statistical outliers. They were treated as interesting curiosities, rather than a way to understand the upper reaches of our own atmosphere. That historical record finally met a challenge from a rooftop in New Mexico. Researchers set up a camera inside a mini-fridge to protect it from the elements, aiming it at one patch of sky for 2 uninterrupted years. From 2021 to 2023, the system recorded every streak of light crossing its field of view, gathering a dataset of nearly 7,500 individual meteors. The results showed a stark difference from mid-century records. The new survey revealed persistent trains occur in 1 out of every 8 meteors. Significantly, the meteor's speed did not dictate whether a train formed. Even slow-moving rocks produced these massive trails. This meant the cause of the glowing trail was independent of the rock's violent entry. The trigger wasn't the meteor itself, it was something waiting in the air. To produce a persistent train, a meteor must reach a very specific altitude, exactly 90 kilometers above the Earth's surface. This height sits just above the main concentration of Earth's ozone layer, where oxygen molecules are grouped into clusters of 3. Passing through this region, friction causes metals to burn off the rock's surface. These metallic atoms then collide and bond with surrounding ozone molecules. This specific chemical reaction generates its own radiant heat and light. This process provides the energy to keep the trail glowing long after the physical rock has disintegrated. These persistent trains are composed of Earth's own atmosphere, energized into a chemical glow that remains long after the rock that triggered it has vanished. Understanding this chemistry gives us a way to study a part of our planet that has remained notoriously difficult to map. While we can measure the lower atmosphere with relative ease, standard weather balloons physically stretch and burst before they can ever reach the 90-kilometer mark. Conversely, satellites in low Earth orbit sit much higher. If a satellite attempted to descend to 90 kilometers, atmospheric drag would pull it down and cause it to crash. In this vertical cross-section of the atmosphere, we see a distinct observational gap between balloon flights and satellite orbits. This 90-kilometer band is often called a dead zone because it remains invisible to our standard instruments. But these glowing chemical trains act as natural probes. By watching the trails warp from the ground, researchers can finally see and map the wind currents swirling inside this unreachable world. One final mystery remains. High-altitude winds are incredibly chaotic, yet these glowing clouds often maintain a tight cylindrical shape for an hour instead of being immediately blown apart. The leading hypothesis points to the dust shed by the space rock. These tiny metallic grains may carry intense electrical charges. These charged grains might generate an invisible electric field, acting like a physical container that binds the glowing chemical cloud together against the wind. For a century, astronomers analyzed these trails to understand the death of space rocks. By finally identifying the chemistry behind these glowing phantoms, researchers established a way to observe the most hidden layer of our own planet.